Hello, everyone, and a very warm welcome to Kognito Key. Today, we're unpacking a fundamental concept in computer architecture that literally affects every single device you use. We're talking about the computer memory hierarchy. If you've ever wondered how your computer manages to effortlessly juggle massive games, complex software, and let's be honest, hundreds of open browser tabs all at once, well, you're in exactly the right place. In this explainer, we're going to break down exactly how system designers perform this incredible balancing act between speed, space, and cost. So get ready because this is going to be incredibly fascinating. So let's kick things off with a pretty simple question. Why not just build one giant lightning-fast memory chip for our computers? I mean, our applications are constantly demanding more and more space, right? Why overcomplicate the design? Well, the truth is, engineering the perfect memory system presents a massive physical problem. There is absolutely no single magic chip that can do it all. And to understand why that is, we have to look closely at the real-world limitations that system designers face every single day. Okay, let's dive into this. Whenever a system is designed, there are three conflicting constraints that constantly go hand in hand. First step is speed, meaning how fast the processor can actually access the memory to execute your programs. Second is capacity, the sheer amount of memory space you have available to store those massive files and applications. And finally, cost per bit, because practically speaking, the memory needs to be affordable relative to the processor and the motherboard. The catch? You simply cannot maximize all three at the same time. These three constraints create what we call the memory trade-off, and it's a direct, completely unyielding relationship. If you want the absolute fastest access time, you are going to pay the greatest cost per bit, and you'll unfortunately get the lowest capacity. On the flip side, if you want a massive amount of storage, greater capacity, you just have to accept a slower access time, though the upside is it'll be much cheaper per bit. A brilliant system designer has to constantly balance these extremes to optimize the overall performance of the computer. So, what's the actual fix? The crucial point here is that the solution is never just one perfect component. The real solution is a memory hierarchy. Instead of relying on a single chip, we organize memory devices into a very structured hierarchy. We combine smaller, very expensive lightning-fast memories right next to the processor, and we supplement them with larger, cheaper, and slower memories further away. The whole goal is to bring frequently used instructions as close to the processor as humanly possible. Let's start right at the very top of this hierarchy. Right at the top, sitting directly inside the processor itself, we have registers. Registers are the smallest memory units in the entire system. They're capable of storing just one single word of data, but they have the absolute shortest access time. Because they're completely internal to the CPU, these high-speed storage elements are used to hold operands, which is the actual data being manipulated the exact moment they are brought in for processing. And this brilliantly illustrates just how specialized these little units are. A processor relies on several very specific registers to function. You've got your instruction register, which holds the exact instruction that's currently being executed. Then there's the program counter, which keeps track of the memory address for the very next instruction the system needs to fetch, and the accumulator, which holds your temporary operands and the results of arithmetic and logic operations. They are incredibly fast for sure, but they only provide a tiny fraction of the memory you need. Stepping just slightly out from those registers, we find cache memory. Cache is the next step down in the hierarchy. It's a small memory unit implemented directly on the processor chip itself. Its main job? To hold copies of recently processed instructions and data. Think of it as the processor's personal high-speed notepad. When the CPU needs a recently used instruction, it grabs it instantly from the cache, totally saving it from making a very slow, repetitive trip all the way out to the external main memory. Now, what's super interesting is that even cache memory is broken down into its own mini hierarchy. We start with level 1, or L1 cache, which is internal to the processor chip and has a blazing fast access time that's almost comparable to those registers. Then we step out to level 2 cache, which sits right between L1 and the main memory. It's still on chip, but slightly slower and larger. Finally, we have level 3 cache. This is the largest and slowest of the caches, sitting out there between L2 and the main memory. To really put this into perspective, let's think about the number 100. Once we step entirely out of the cache and reach the main memory, which you probably just know as RAM, the access time jumps significantly. In fact, accessing main memory can take up to 100 times longer compared to accessing that primary L1 cache. This perfectly highlights why cache is absolutely critical for your computer's speed. If the CPU had to rely only on RAM, your fast processor would just spend most of its time sitting around, waiting for data to arrive. Finally, let's look at the absolute bottom of our hierarchy. This is where we find massive, dirt-cheap secondary storage. We have the magnetic disk, which gives you huge amounts of storage but has a much, much longer access time than RAM. And right at the very bottom, we have magnetic tape. With the longest access time of all, magnetic tapes are highly portable, non-volatile memory, meaning they keep all their data even when the power is off. They're used mainly for backing up massive files and records rather than active processing. They're slow, yes, but incredibly cost-effective for large-scale data. So, we've journeyed all the way from the lightning-fast registers inside the CPU right down to massive magnetic tapes. It's just a brilliant balancing act of physics and engineering. But I want to leave you with this final thought. As our AI models and applications demand exponentially more space and speed, how will future systems bend these physical constraints? It's a huge open-ended question that engineers are constantly trying to solve. Thank you so much for joining me to explore this today. If you found this explainer helpful, please do subscribe to the Kognito Key channel, and make sure to like and share this video with anyone who loves learning how things work. See you in the next one.